millions, even billions of miles away, Voyager photographs and transmits a galaxy of stunning images back to Earth. Photographs that allow scientists to study and understand our solar system in ways unimaginable just a few decades ago. Consider for a moment that these amazing images are transmitted through space on only 20 watts of power, the same as the tiny bulb in your refrigerator. Consider also that Voyager's signal must contend with all kinds of interference, noise that can distort or even obliterate the simplest of messages. How does Voyager manage this seemingly impossible task? What mathematical miracle makes this possible? And how are simple geometric curves used to detect and correct errors from these faint signals in space? Robert McElice, mathematician, professor of electrical engineering at Caltech, and consultant for NASA's Jet Propulsion Laboratory in Pasadena, California, has worked on solving this problem.
Well, the first thing to know is that Voyager doesn't transmit photographs to Earth directly at all. It transmits a sequence of zeros and ones. It first converts the photographs using what's called a binary system into a whole bunch of zeros and ones. The way it does is it takes a photograph and breaks it up into a whole lot, exactly 640,000 to be exact, a whole lot of dots, and each one of these dots carries a gray shade. Now, the pictures you actually see on TV are mostly in color, but that's an artifice. A color picture is made by superimposing 3 black and white pictures that have been photographed through 3 different color filters, and then combined on Earth it looks like a color picture. Also, the shades of gray that I mentioned, there are exactly 256 possible shades of gray, ranging on the one hand from pure white all the way to jet black. But for purposes of explanation, you may as well assume that each dot of these many dots on photographs is either white or black. A black spot is represented by a 1, and a white spot is represented by a 0. And so a Voyager picture is taken, let's say in black and white, converted into 640,000 zeros and ones, and it's those zeros and ones that are actually transmitted the millions of miles through space back to Earth and then reconverted into a photograph. Let me give you an example. Voyager's out there right now somewhere, I don't know exactly where, but it's always sending back zeros and ones. So let's say one day we get a bunch of zeros and ones back. We don't know what they're going to mean, but we know what to do. We put the zeros and ones in a photographic grid. We change the zeros to a white spot, the ones to a black spot, and we find out something new. Gee, I didn't know that was out there.
Of course, Professor McElice is daydreaming. But noisy channels left alone could produce a variety of unbelievable images. In the early days, scientists believed they could deal with noisy channels by developing more sophisticated transmitting equipment. But that solution created other problems, problems of weight and cost. Could there be another way? Professor McElice.
Yes, there is another way. It's entirely possible to communicate reliably and rapidly over any channel, no matter how unreliable it might seem to be. This seems too good to be true, I know, but in 1948, a mathematician named Claude Shannon, who at that time was working at Bell Labs, just astonished the scientific world by showing how it could be done. Now, before Shannon, you sent your data over the channel, and if it came out an error, too bad, there was nothing to be done. Shannon's idea is to process the data before transmitting it by passing it through a device which he called an encoder. Now, the encoder's job is to produce extra data. This extra data is called redundancy, and then add the redundancy to the original data and transmit it over the channel. Now, this is a subtle and a tricky concept, and it's the key to everything that Shannon has done. But the most primitive form of redundancy is simply to repeat the message over and over again. Shannon's ideas are not that trivial. We'll come to an example later. Then, after the data plus the redundancy are combined, that combination, which is called a code word, is sent over the channel. Now, the channel may cause errors in the data, it may cause errors in the redundancy, or very likely both. But there's such a strong pattern in the data plus the redundancy that if this combination is passed through another device, which is called a decoder, that pattern will still be recognizable, and the original data ought to be recoverable. At least that's the idea. Shannon was a real theoretical type of guy. He never said exactly how these encoders and decoders should be built. He only proved that it must be possible to build them. But that's okay. The challenge was taken up by later generations of mathematicians and engineers, and today there's hundreds of applications of error-correcting codes. One of the first practical examples was made by Richard Hamming, who is a colleague and a contemporary of Shannon's working in Bell Labs in the late 40s. And Hamming codes, as they're now called, are used in a lot of computer applications. They protect the computer memories. But I would say that today the most important single class of error-correcting codes are what are called the Reed-Solomon codes. Reed-Solomon codes have a tremendous number of applications, including applications to Voyager's telecommunication system. Reed-Solomon codes were invented in 1960 by Irving Reed and Gus Solomon, who at that time were at MIT Lincoln Laboratories. I can explain the basic ideas of Reed-Solomon codes with some simple geometric arguments, so let's work an example. Now, Reed-Solomon codes work ultimately with zeros and ones like most of these systems, but in order to explain what's going on, it's easier to think of ordinary numbers. So in the illustrations, we'll be dealing with ordinary numbers, but bear in mind, it's really all zeros and ones. Suppose we wanted to send two numbers, let's say 3.6 and 5.9, from one point to another over a noisy channel, and we wanted to use Reed and Solomon's ideas. The first thing to do is to plot these 2 points geometrically. Okay? We all know that any 2 points determine a straight line, so we draw the straight line through those 2 points. Now, we started with just 2 points, but of course the straight line contains a great many other points. So let's choose 4 more of these points as the redundancy for our code word. Let's choose 8.2, 10.5, 12.8, and 15.1, which are 4 equally spaced points on the straight line. Now our code word will be formed of the 2 data points, 3.6 and 5.9, and the 4 redundancies. So the overall code word is 3.6, 5.9, 8.2, 10.5, 12.8, and 15.1. There's a very strong, where the original data had no pattern, but now there is a very strong pattern. These points lie on a straight line. Now if we send this data over the channel, we might have some errors. Let's say, just for an example, that the 3.6 and the 5.9 are interchanged, and we receive 5.9 and 3.6. You can see that the straight line pattern has been spoiled, but not entirely obliterated, since 4 of the 6 points still lie on a straight line. But if we draw a straight line through these 4 points, we see that 2 of the points aren't on the line. But since we know that the transmitted points all began life on a straight line, in order to recover from the errors, all we have to do is move the wayward points back onto the line, and presto, the original code word appears. The errors have been corrected. That was one example of Reed-Solomon coding, an example where we took 2 numbers using the Reed-Solomon's idea and tried to transmit them reliably over an unreliable channel. But in practice, of course, you might want to send a lot more than 2 numbers. The next example to consider is suppose we wanted to send 3 numbers over a noisy channel. How would we do that? Well, suppose we wanted to send 3.6, 1.2, and 2.2 over a noisy channel. The idea is to again plot the 3 points geometrically. Unfortunately, 3 points won't lie on a straight line in general, but any 3 points will uniquely determine a parabola, which is a second-degree curve. So now let's draw a parabola through these points. Now that we have the parabola, it's easy to guess what to do next. We locate some more points, let's say 4 more equally spaced points along the parabola, and use these points as the redundancy, thereby producing a 7-number code word: 3.6, 1.2, 2.2, 6.6, 14.4, 25.6, and 40.2. The original 3-number data had no particular pattern, but this 7-number code word has a very strong pattern indeed, because the 7 points all lie on the same parabola. It's extremely unlikely that 7 numbers chosen at random would lie on a parabola. With 4 redundant numbers, again protecting the data, we can correct any pattern of 2 errors. For example, suppose our parabolic code word were received with errors in the 1st and 5th positions as 11.6, 1.2, 2.2, 6.6, 3.3, 25.6, and 40.2. Now notice in this example, an error occurred in one of the data numbers, namely the first, 11.6, and also in one of the redundant numbers. We can recover from that as well. In order to do that, we plot the 7 received numbers with their errors geometrically and look for a parabola connecting at least 5 of them. In this case, it is a little difficult for us humans to see the pattern, but the decoder or the computer doesn't have any trouble and can find the majority parabola immediately. 2 of the points don't lie on the parabola, so the decoder moves them back on, thereby again correcting the errors. course, the real world is always a little more complicated than these examples, and in fact, in the NASA system, which is used by Voyager, the Reed-Solomon codes are used to protect blocks of exactly 223 numbers simultaneously. And in order to do that, it has to use a geometric figure formed by a 222nd degree polynomial. But those are all mathematical details. The basic underlying ideas are geometric and just the same.
As Voyager travels through space, it continues to photograph and transmit extraordinary views of our solar system, thanks in part to the work of mathematicians like Claude Shannon, Irving Reed, and Gus Solomon. But what about the future? For young mathematicians interested in the field of error correction, what challenges lie ahead?
Shannon would tell them that there are a lot of possible opportunities to apply his techniques to channels. And he would tell them something strange. He would tell them to look for channels which are quiet, not channels which are noisy. That sounds contradictory, but let me explain that a little bit. Shannon says that if there's a channel which seems not to be making any errors and you're happy with your transmission, it could be cable TV, it could be telephone conversation, could be anything, and it seems to be working well, you're fooling yourself. You're not pushing that channel hard enough. To get the most out of any channel, you drive it as hard as you can. You talk faster into the telephone, or you put more bits on your magnetic recording until the channel changes from a quiet channel to a noisy channel, and then you correct the errors caused by the noise using his ideas. When you take that point of view, then it's easy to see potential applications for coding. You look for quiet channels or channels that seem to be okay. Cable TV, cellular telephones, certain kinds of magnetic and optical recording. Compact discs use Reed-Solomon codes, and it's a very recent application. There are a lot of opportunities for coding.